global warming. And whenever I present now some data, I will only quote scientific work that has been published in international journals and that was peer-reviewed, how is it called. And now to the crucial question, the relation between CO2 and warming. What we are told is when CO2 increases, then the warming adds up. And let's look at the data again. I have shown you this curve already. This is from these ice core drills. We see these fluctuations. And now, as I told you, from the air bubbles inside the ice cores, we can also get information how much CO2 was in the atmosphere over this time scan. Here I give you again this relation. 100 ppm is 0.01%. You see, that's the reason why we don't use a percentage as a number, but the ppm. And this is the data. And if you make a short glance at it, you can say, oh yes, we see very clearly the CO2 is rising, temperature is rising, CO2 is rising, it's going down. There's a strong relation between CO2 and temperature. But you have to look very carefully. Look at these lines here. The blue line is starting first, it goes up, and then the CO2 follows afterwards. And this has been subject to many research works, and they've looked into detail into these curves. Here you see the temperature from this peak at around 235,000 years ago. And here you see the CO2 curve. And here you see it already clearly. First the temperature goes up, and then CO2 starts. CO2 goes down, temperature goes down, not so in correlation. There are other effects that it does not go down so drastically. But here you see it very clearly. First the temperature goes up, and then the CO2. And if we look at this absorption spectrum of CO2, we see that this broad line that actually makes the main absorption of CO2 is already saturated. And this is known to the Deutsche Bundestag, to the German parliament, already since 2020 by their own scientific service called the Wissenschaftliche Dienst. They published a special report on this fact. And the translation, it is in a version of 2023, but it's only the wording of other parts of this report were changed. This means that additional carbon dioxide entering the atmosphere will have no effect on the absorption in that portion of the band, that means this 15 micron band, because the carbon dioxide in the atmosphere already completely absorbs the wavelengths in this portion. And this is known to the German Bundestags since 2020. And to the IPCC, this is known since 1995. They had a special report of more than 380 pages where they say, at the center of the 5 micron band, that is this wide area, the increase in CO2 concentration has almost no effect. The CO2 absorption is indeed saturated at these wavelengths. That's something. You know it since 1995. Actually, the physicists that are working with spectra knew it even longer time. But this is officially in their report from 1995. And now we have looked at the individual gases, but in the atmosphere all these gases are mixed. So we now, from the same work, now we see here, we add ozone and oxygen, we get this absorption, we add the nitric oxide, and now we add methane. And I want to put your attention to this methane peak here, this absorption. If we go back, at exactly the same point there is an absorption peak of nitric oxide. And this nitric oxide roughly absorbs 70%, and this peak absorbs 80%. We cannot add this together. 70 plus 80 would give more than 100%, 150. We have to do a different calculation. We have to say this absorbs 70%, therefore 30% are left, and from this 30%, 80% are absorbed by the methane. So all in all, 94% are absorbed, and only 6% go through. This is the combined effect of these two gases, and it is not, we can calculate it the other way around. For the light, it is completely indifferent to which gas absorbs it. Once it's absorbed, it's not in the light beam anymore. And if we add now CO2, we see this effect. And if we add water vapor, we see this strong effect of water. And this effect is called overlapping. You see here? If we now increase CO2 in the atmosphere, actually, since this peak is already nearly, or this band is already nearly saturated, we get a steeper edge here, we can add some of this white color will turn red. But on the other flange, nothing is happening because there's a lot, 100% of the incoming radiation at roughly 20 microns is already absorbed by water. And look, do you see any green anymore from methane? Yeah, here you see it. It is completely overlapped by water vapor. And now this is just the potential of the atmosphere to absorb light, and now we have to factor in at which wavelengths is actually light entering the atmosphere. And I showed this already to you. In this range here, nearly or hardly any light is entering. So this very strong absorption capacity of the atmosphere and also the methane, they don't add up to heat. It's not converted to heat because simply there is no light entering the atmosphere in this wavelength range. And the overall effect now is this. This is the light going into the atmosphere, and it is the light going through the atmosphere. And in all places where you see the white, there is light not present anymore. That is converted to heat, and you see this drop is from this peak here, from this oxygen peak, and these strong drops are from these water peaks. And here you see this white area, that is all of the light that does not exist anymore, therefore it's converted to heat. This comes from this huge water band, and on this side you have the combination of the water band and the CO2. This gives this very sharp drop here. And this one from the oxygen, you see this drop here. And now you can ask yourself again, what happens if we add CO2 to the atmosphere? More or less nothing. Where should it come from? If this peak becomes a little bit sharper, okay, first it is not much, it will become a little bit broader and sharper, but there is hardly any radiation entering the atmosphere, so the actual heating does not take place, simply because there is no radiation there. And also you see the nitric oxide, there's a strong peak here, it's a narrow peak but strong, but again, this is in a range where there is no radiation entering the atmosphere, so the contribution of nitric oxide is zero, more or less zero. And if we ask the question, what would happen if we add more water vapor to the atmosphere? Okay, all these peaks will go up, not here, it is saturated, this is nearly saturated, but these peaks will go up. But here, we have the overlapping in the other way around between water vapor and CO2. So if these peaks go up further, there is already 100% of the light is absorbed and converted to heat by the CO2. So the only thing that is left is this water vapor peak and this water vapor peak. That means this one and this one. And if we add ozone, okay, this peak becomes a little bit higher. This becomes less light goes through, therefore it's converted into heat. And I let this now rest. You have to look at this. This explains the greenhouse effect. And this explains you the effect of the adding CO2 to the atmosphere. More or less nothing. There's nothing left, there's no process. Where should this extra heat come from? And that all the politicians should look at this graph. And I will present this graph in the Austrian Parliament. I'm invited to give a very short talk. And I will present in this graph. Where should the heating come from? There is no process. It's all saturated or overlapped. And this was investigated by a group of very good researchers very recently in 2000. Before I do that, I have shown you that the overall greenhouse effect gives a temperature increase of 33 degrees Celsius. And we can break this down. What is the contribution of water vapor? 29.4 degrees because of these huge blue areas that I showed you. The CO2 makes only 3.2 degrees Celsius. It's just this small part of red that you could see shine through. And the combined effect of methane and nitric oxide is negligible. It's 0.3 degrees Celsius. It's nothing.